As I mentioned in my last video about Kotlin's Flow API, we can put our emitter and collector on different coroutines by using the flowOn operator and passing it a dispatcher that's different from the one that the collector is already using. And once we do that, the emitter and collector no longer have to run in tandem. The emitter doesn't have to wait on the collector before producing its next value. But what happens to those emitted values when the collector isn't ready for them yet? For example, in this code, we've got a 5-second delay in the collector, but you'll notice there is no delay in the emitter. So the emitter is definitely going to produce values faster than the collector can keep up with. Well, by default, when this collector isn't ready for the next value, then any values emitted are going to be simply accumulating in a buffer that holds up to 64 values. And then once that buffer is full with all 64, then the emitter is finally going to suspend and wait on the collector. Let's give this a run to see this in action. As we can see, the first 65 values are emitted. Remember, it's starting with 0 and getting up to 64 for a total of 65. And that's because the collector is processing the first value, and then the buffer fills up with 1 through 64. Then as the collector receives the next value in the flow, this makes room in the buffer for the next value, so the emitter runs again, and that just kind of keeps happening for the rest of this run. So when we use flowOn to configure our flow to run on multiple coroutines, the default behavior is to buffer up to 64 values in the middle. Now, it is possible to configure that default buffer size globally, but more often we'll want to customize the buffer size for each particular kind of flow. And here's how we can do that. The code you see here is very similar to the code that we just looked at, but you can see I've chained the emitter and collector directly together into a single expression. Now, we've already seen how the flowOn operator can configure our flow so that the emitter and collector run on different coroutines, but we might want our flow to run on multiple coroutines without changing the dispatcher. Well, there are a few different ways we can do that. For example, we can simply use an operator function named buffer like this. And we just pass it the capacity that we want it to have. And this splits our flow so that the first part runs on one coroutine and the second part runs on another. So this puts both coroutines on dispatchers.default and uses a buffer with a capacity of 5 instead of 64. And by the way, for those cases where you want to set a buffer size and the dispatcher, you can just chain them directly together like this. Now, typically when we call buffer or flowOn, it causes a new coroutine to be introduced. So you might be worried that in this code, we would end up with 3 coroutines here. But the Flow API is actually smart enough to notice when these two operators are next to each other, and they'll undergo a process called operator fusion so that they can act as if they were a single configuration. So the result is that this still just runs on 2 coroutines, not 3. So again, one way to deal with an emitter that moves faster than a collector is to use buffering. But we have other options too, like conflation. With conflation, instead of holding excess values in a buffer, it holds on to just a single value, and any other values are going to get dropped. We can just use the conflate operator like this. Now, the cool thing about conflation is that the emitter will never need to wait on the collector. If the collector isn't ready for the next value, well, too bad. Ready or not, here it comes. If there's a value that the collector hasn't picked up yet, it'll just get dropped. So the collector only ever gets the latest value. Let me give this a run here. We'll see that the first value is going to get emitted, and while the collector is delaying for 5 seconds processing that value, the other 99 values are emitted. And then finally, after the 5 seconds are up, we can see that the collector processes that latest value, which is 99. So buffering and conflation are 2 ways that we can manage an emitter that's moving faster than a collector. Let's look at one more option, which is debouncing. The behavior of buffer and conflate is based on the volume of values that the emitter produces. But there are some occasions when we'd rather base it on the amount of time that's passed since a value was emitted. So the classic example of this is when we've got a text box with autosuggest, where we call the server to do a search as the user is typing. And here's some code that simulates that experience. So the user is going to type this term here, and we'll call a service to find results for that query. And I've added some logging all along the way so that we can see what the user has typed, when the service was called, and so on. And just so you can get the full context, let me scroll down here just a little bit. You can see we've got this service object that's simulating a remote service, but here it's just in memory. You can see we've got the search for function here, and it's a pretty simple book model. So back up here in our main function, when we run this, we'll see that we're calling our service 9 times. That's once for each keystroke. So we're totally bombarding the service this way. To remedy this, we want to prevent the collector from receiving any values until we know that the user is probably done typing. And this kind of operation is known as debouncing. If you've ever done any work in microelectronics in the past, you're probably already familiar with the term. When you turn on a light switch, for example, there's a brief moment in the middle of the switch where the contact is kind of bouncing back and forth between being connected and not being connected, and that's called bouncing. So debouncing aims to remove that effect so that there's a very clear distinction between the switch being on or being off. Well, the Flow API can debounce the values by waiting to emit a value until the upstream flow has been silent for a certain amount of time. To add a debounce, we just include a call to the debounce operator like this. So with this flow, the emitter can send values as they occur, but the collector won't get them until the emitter has been quiet for at least 250 milliseconds. And once that happens, the collector will just get the latest value. And by the way, this operator is still considered to be in a preview state, so I'm just going to opt into it up here like this. When we run this again with the debounce, we'll see that even though the user typed 9 characters, we only ever called the API once after the user was done typing. So again, it's possible for the emitter to outpace the collector when a flow is running on multiple coroutines, but thanks to buffers, conflation, and debouncing, we've got several strategies to make sure that our collector receives the values that we want it to. Well, I've got one more video planned for this series about Kotlin's Flow API, where we're going to take a look at how we can manage exceptions in our flows. Also, if you've got any questions you'd like me to answer about the Flow API, just add a comment to this video with your question. And I've still got your questions from some of the earlier videos in this series as well, and I'm going to start assembling those into some Q&A videos. So again, if you haven't already asked your question, go ahead and do that now. Also, be sure to like this video, subscribe to this channel, and share this video with that special Kotlin developer in your life.